Good morning. So it's a pleasure for me to introduce Michele Vallisneri. So Michele was here in 2019 as D'Alembert chair, and some of you may remember him for giving a beautiful course on Python. And he's back now for this course on gravitational waves. So just for those who don't know him, Michele earned his PhD at Caltech with Kip Thorne, and then he did a postdoc there. And in 2005, he became a researcher scientist at JPL, where he's now as a senior research scientist. So Michele has worked basically on all possible experiments on gravitational wave physics, more or less. So he was part of the first detection papers by Ligo on gravitational waves. He's part of LISA. He's heavily involved there. He's co-chair of the LISA Science Group and the LISA Data Challenge. He was one of the main organizers of the mock data challenge, and he's now involved in PTA, in particular on the data analysis for nanograph, and he's seeking to make the first detection of low-frequency gravitational waves. So I think that Michele, the chair,
Thank you. Thank you
the
very
floor
much.
is yours.
So it's good that these are supposed to be in English, so I can be a little more comfortable. But enchanté d'être ici. C'est la France, c'est un peu une seconde maison pour moi. Et Philippe was here. So I think you may have gone to courses about gravitational waves already, and it's both a bit daunting to do something like this because at this point the subject matter is huge, but also I don't want it to be especially boring for you, given that you're not students, you're professionals. Okay, so I think a useful way to do it, since I'm not Fermi, and I'm not Amaldi even, but I'm flexible. So I think a way to look at this is at a way to explore the interface between astronomy and gravitational wave science and theoretical physics, which is what I think a good chunk of you are. So let's keep it interactive. Intervene when you have questions or comments. There will be things that you probably know better than me, in which case I would welcome you to clarify or finesse points. Also, especially today, maybe toward the end, but in general, if you have topics that you're interested in, I have laid out some topics in the scheme of the course and on the poster, but we can change that, we can add them up, and I have reserved quite a bit of time in June to prepare this and look at this. So there are things that you'd like. They would probably be good for me to learn also, to know about, so I can go and look at them. So just please let me know. Yeah, so your questions may also become topics next time if I think that they're better addressed with some time. And now I do feel a bit better because Luc is not is not coming. Luc Blanchet is not coming to these, since he would be one to give lectures about gravitational waves and in particular talking about post-Newtonian expansions and post-Newtonian solutions in front of Luc would be very intimidating. But anyway, so let's try to start. So a few years back in 2016 was a big change for our community, for astronomy in general, but certainly also for the lives of many of us, and also for the way that we gave talks and lectures, because we used to just give basically theoretical lectures talking about what are gravitational waves, what we're going to see, what are our prospects, our future. And finally, we could do the opposite. We could say, look, this is what we measured. Let's see what it means, and let's try to explain it. So that was a big change, to be going from promising things to actually have to explain things, to go from theory that one day would be experimental to experimentalism, experiences that become that have to be interpreted in times of physics. I must say that when I was a PhD, this transition had been promised for much earlier. So when I was in graduate school, LIGO was about to start its initial measurements. That would have been around 2000 when it first switched on. And I think people had convinced themselves that it would see things the first day, right? And that hopefully nature will be generous enough to have something to see in the initial LIGO, initial Virgo. So that was not the case. We had to wait until really the 10 times better sensitivity, basically, and something like 15 years, which was a long time to wait, right? But here we are. And so that was what was seen in September 2015 by the two LIGO interferometers. Virgo was not quite measuring back at the time. In fact, the signals were seen at the very end of the engineering run, just before the start of the official science run. But luckily, the instrument was in science mode when these were seen, and so it was possible to analyze the data as if it was science. So, so a nice exercise is to just look at this very phenomenologically, with that as little theory as possible, and to try to see what we can tell. So there's been a couple of good papers, one by the LIGO collaboration, another one, I'll look it up for you, I can email you, about interpreting the signals using only basic physics, which I think is fun. It's a fun thing to do. But for one thing, we see what we see here is a spectrogram of a time frequency spectrum. So you have time going on the x-axis. You see it's only half a second. It's not a long time. You have an extraction of power as a function of frequency on the vertical. And so one see two signals that are starting at relatively low frequency, and then they are chirping up. Chirp is this technical word that describes just the signal increasing in frequency. Then they stop at some points. They seem to be whitest, so the most power around something like 100, 150 maybe hertz. The other thing that's striking is that the two LIGO interferometers, which are separated by, I forget, what is it, 2,000 kilometers, maybe 3,000 kilometers. So they're almost aligned, but in rather different parts of the US, even culturally different, Louisiana and Washington State. They see pretty much the same signal. So I think one can, I think the waveform at the bottom maybe has been flipped, because there's known to be, although they're aligned, they have a 90-degree turn between them. But otherwise, this seems interesting. There's a signal. It's confirmed by seeing almost the exact same waveform in two very separated interferometers that don't share anything. So when I actually showed this at a talk for elementary school students, well, maybe they were middle school, I don't know. There was this 10-year-old girl who said, "Hey, but look, the blue one is shifted with respect to the red one." And I said, "Oh my God, you should please come and be, be my research assistant, because that's exactly what it is, right?" So if you try to align the phase of this signal as best as you can, you get a delay. What is it? About 0.07 seconds, I think 70 milliseconds, which you can interpret as the time of flight of a signal traveling at the speed of light at some angle with respect to the two interferometers. And of course, that very delay is what gives you a profile in the sky, a contour of where the source, if it is again a source at the speed of light, may come. So then I do have these episodes where I get moved by things like that. Also, like a month ago, so my son is now 12. Okay, at 12 they finish elementary school, and so among the other things they do career day, where parents are supposed to go and talk about what they do, and so the kids can go to different ones. And a 12-year-old, boys are not very smart. They mostly like Minecraft. They're like, but the girls are amazing, right? And so there were these two blonde twins, Okay, so they already look very smart and so on, and so I give them the whole thing, gravitational waves, they're out in space and so on, and one of them then asks, but so looking at that waveform, how can you tell how far the source was? And again, I was, oh my God, that is Schutz 1978. It's a Nature paper, and I can't really explain it to you. But you look at this chirp mass, this thing, and then and please, in a few years, please date my son, because because if you're not going to be a physicist, maybe at least you can meet my daughter-in-law. And I remember this forever. So that we're going to look at, actually, how to answer that question. I couldn't do it with her because after all, she doesn't know algebra or differential equations and all that. But anyway, so common physics. Okay, so pictures a little bit distilled down. On the left, you can see again a superposition. What's impressive is that the signal there wasn't much done to it. So all that was done to these two signals there was a band passing, effectively.
So you may point.
I can point. I can point.
No, yeah,
I can point with this.
Yeah.
So so all that was done to these signals was some band passing. So otherwise, there's lots of high frequency noise. There's some kind of low frequency behavior that would somewhat obscure that. But if you just do a simple filter to the signal and let go frequencies between, I don't know, 50 and 500 hertz, that's what you get. There's a shift, the famous 8-year-old girl, always girls, shift between them. And now, what is this? Okay, just on the basis of the signals, what is this if you don't have the 100 years of theoretical development from Einstein's paper on gravitational waves up to the present? So I think one can do some simple arguments to show that the signal was emitted by two black holes that were spiraling and then merging. And one can even get out a total mass from this and a luminosity distance. So how do you do that? So just phenomenologically, what you observe is that you have a signal that looks roughly sinusoidal for something like 8 cycles. Okay, you see that the amplitude is rising up. You see that the frequency is also increasing, so that at about here, it reaches a maximum of its amplitude. And if you just measure the time between the crossings, the 0 crossings of the signal, you can measure this maximum amplitude frequency as something like 150 hertz. Okay, and then then it does a couple more cycles. It's going down already. The maximum frequency that it achieves is about 200 hertz. And after that, it dies out. Maybe it rings out. Maybe there's some oscillation there. Maybe it's noise. That's not entirely clear. Let's see. So frequency increasing, stabilizing, amplitude maximizes and then decreases. So what is this? It's probably not a perturbed system that's returning to equilibrium. If it was something like a bell or some kind of oscillator, you'd expect it to keep a constant frequency more or less. And you'd expect actually to have the excitation at the start and then the amplitude going down. It's also not a system, if it's some kind of astrophysical system, it's not a system that's conserving angular momentum, because with that you don't get quite this frequency evolution, although we should see that. So if we're just saying, okay, we have gravity, let's do pre-1916 theoretical physics. We have special relativity, we have gravity. So there must be some kind of traveling excitation of gravity, some wave of gravity. In fact, if you look at the history, who had been going at gravitational waves before Einstein? I should know this, but I think Poincaré had looked at them, and perhaps even Riemann himself. So say, okay, maybe it's a wave of gravity, right? We've designed this experiment basically to be sensitive to gravitational interactions by way of tidal fields. We have 3 masses. We're kind of comparing the masses. We're doing Michelson-Morley experiment, more or less. We're comparing the distance between, the relative distance between 2 masses. This is going to be sensitive to things that push the mirrors of LIGO with respect to each other. So a wave of gravity, then what would it look like? Oh, thank you. I've done this before. Okay, so this is my only blackboard thing. So, you know, let's call it H. Now let's use it. So it's a wave, it's self-propagating, it probably carries energy like most waves, so it will have to go at something like 1 over radius if we're looking at the potential. Okay, we describe a potential. And now, what can generate a wave of the gravitational wave interaction? Well, you think it could be mass. Okay, after all, the charge for gravity is mass. However, to generate a wave, if we think a gravitational, if we think electromagnetic waves, you have to put some kind of derivative. You want a moving mass and changing mass, time-dependent mass, and we can't quite do that, right, because of conservation of mass. So that probably doesn't work. What's next? Next could be dipole, mass dipole, and see if we can put a derivative on mass dipole. That would be really an analogy to electromagnetic waves in an antenna or something like that. Also, we cannot do that because mass dipole is just momentum, basically, and the derivative of mass dipole. Momentum, that also we cannot change for an isolated system, as we think could be the source of this. So the next thing that we can have then is mass quadruple. So then, okay, mass quadruple. What derivative should we put on there? So let's try good old dimensional analysis, which one keeps discovering in the course of one's career that is the best friend of a physicist. Okay, so and let's work in the units that are easiest for gravitational interactions. So let's set Newton's constant equal to speed of gravity equal to 1. If that's the case, and also we're talking about strain, we're talking about a relative change in distances. So we need basically a dimensionless result here. So what kind of what do we need to do this quadruple in order to get a dimensionless signal in strain? So I have 1 over length. Mass quadruple is going to be like mass over mass times length squared. The quadruple as we're saying, so it's going to be something like an object like this, right? Quadrupolar. So mass density times the integration goes into mass and to length. So to go from, but in geometrized units, mass and length and time are all the same thing. So this is really length cubed. So to go down to dimensionless, given the 1 over the distance, we need to do this. So this is basically Einstein's quadruple formula, just done from dimensional analysis. So then we're saying that H will go as something like 1 over V Q dot dot. Okay, so however, let's see what more we can do. Let's say what could then be given a time-dependent mass quadruple somewhere out in space. If you do the, again, just we do geometrized units, so we want an H that's not infinitely small or exceedingly small. We're going to need something that is heavy, that moves fast enough, that is accelerating fast enough, and that can get quite close so that we get high enough frequencies. So a binary can be a compelling explanation. There are many binaries in astronomy, many in the sky. And a binary could be a system that gives this frequency evolution that we were talking about, since we assume that emitting gravitational waves is going to take energy from the orbital energy of the system, send it out to infinity. Doing that, subtracting energy, the binary will shrink. Shrunken binary by Kepler's law will give you faster evolution, and so forth in an accelerating way, which is what we see. So if then you introduce Kepler's law, And I think Kepler would be quite proud to still make it into physicist blackboards even a long time after it was carefully doing that. You can take this and you can figure out what the quadrupole moment is for a binary. It's going to be a reduced mass times simply the orbital velocity, radius squared, omega squared. And that we can actually also write as 1 over d. Actually, let's write it as mu over d times m over. Just using Kepler's law to go between angular velocity and just orbital distance. So what do we say here? Since I seem to be in a mood of doing stories today, I can tell you another one, which is when I did my candidacy, which is what you do in the US doing a PhD when you have to show what you're going to do eventually for your research. I got into this kind of formula, and I was getting a little tied up by various powers and so on, and until luckily one of the professors say, "Oh, that's just Kepler's law, so let's not bother about Kepler's law. Let's keep that. Let's assume that works out." But I think what's interesting here is that I don't know if it's quite dimension analysis, but Kepler is what gives you the Chirp mass. Okay, if you look at this gravitational wave literature, there's a somewhat mysterious combination of masses, reduced mass to the 3/5 times total mass to the 2/5. And this is known as the Chirp mass, and it's the thing that gives you that frequency evolution. And it gives you the possibility of measuring the distance to a source just from its frequency evolution that the 12-year-old girl, blonde, was asking about. Okay, so when
can you define a mu?
Oh yeah, so mu is reduced mass, is what is the combination of masses that comes out naturally in a binary. M is total mass, and 1 plus is 2. And now there's a curious combination of them, 3/5 times 2/5, which is known as the Chirp mass. And so if I use it here, I guess that I get that this gravitational wave strain from dimensional analysis is equal to a combination of is a Chirp mass over distance. So the amplitude scales with distance and Chirp mass, and then frequency, that's orbital frequency still, times Chirp mass to the 2/3. That's just Kepler, okay, bringing in this 1/3. So what's interesting here is that if we were just writing the total energy of the binary, which is minus 1/2 mu m over r, orbital separation, m is total mass, comes from Kepler's law, and mu, since it's reduced mass, it's the way the two masses in a binary combine to act as a single effective mass, effectively. So you see, it's the same, except for the distance, for the distance to the source, it's the same combination of masses. So this also we can write in terms of the Chirp mass. And it looks like minus 1/2 Chirp mass times Chirp mass orbital frequency to the 2/3. Okay, so from this, we already see that if we're losing energy to gravitational waves from orbital energy, the resulting process is going to scale exclusively with Chirp mass. That's the only relevant length scale here, and it's not either one of the masses. So if you do that, we need a little more jump of little bit leap of faith in dimensional analysis, which is the luminosity must scale as something like the surface of a sphere at your distance, times the square of the strain. The first derivative of the strain squared. So this comes from requiring the right units for luminosity. It also comes from analogy to electromagnetic waves. And then from this, one can go on and write something like the evolution of energy in terms of the derivative of the orbital velocity. It's going to be minus the luminosity. And this eventually leads you to something like Fermat squared times omega dot. This omega dot is Fermat omega to the 11/3. You can also write this as a combination of omega dot omega equals the certain power of the Chern mass. And then there's going to be a constant here that is actually 7,000, and it turns out this is a little bit misleading because you shouldn't get a constant like 7,000 in dimensional analysis, but it's really here because of these high powers. So you can write a more natural, I should have written a more natural relation here that has a constant of order 1, which is really that the Chern mass is of order 3/5. Okay, so here we are. Define one last way to write this. The omega dot omega to the minus 8/3 is of order Chern mass to the 5/3 times t. So that's what this plot is about. Okay, finally coming back to the slides. So plot on the right, we're showing frequency to the minus 8/3. We expect this to have a roughly linear evolution in the course of the binary. And by fitting the constant of this linear evolution, we get Chern mass to the 5/3. And that in the interpretation that we're just seeing a binary and that somehow we're emitting energy to the quadruple is our binary Chern mass. So the resulting fit to within 30%, because those points are a little bit all over the place, is a Chern mass of about 30 solar masses. If you use that equation and turn it into, for instance, into mass for two equal bodies in time spiraling, they each end up at about 35 solar masses also. Okay, so two stellar objects in spiraling, following a law that seems to come out from a generic idea of gravitational wave or gravitational theory. How close are they getting? So we know that the maximum frequency is about 150 hertz. One more thing that I could have told you is that we're looking at a derivative of quadruple. Quadruple in the binary is actually comes back into itself after a turn of 180 degrees. Okay, that in your theoretical physics, you'll see that at a spin 2, manifestation of spin 2. So that means that the frequency that we see at gravitational waves would actually be twice the orbital frequency emitted for radiation emitted by a binary. So if I then can try to solve for the equivalent orbital separation, I was using small r actually. This is going to be something like 70 solar masses, total mass, times frequency squared, so pi 150. This is seconds to the -2 squared to the 1/3. So we get something like a closest approach of 350 kilometers. Okay, this just if you work through the units, in a solar mass in geometric units, you can either write it as 1.5 kilometers or as 10 to the -5, 10 to the -5 seconds, 5 10 to the -6 seconds, sorry, 5 microseconds. This is 2 pi times the pi times the maximum frequency gets us the maximum angular frequency together, 350 kilometers. Okay, so that is very small for stars, right? So sun is, what is it, 1,000,000 kilometers? I don't know, 700,000, something like that. Even white dwarfs are 1,000 kilometers. So there would be several times that. Neutron star would be maybe fine, because a radius of a neutron star we think is 10 to the 15 kilometers. However, we've seen that the mass is on the order of 30, 35 solar masses. We think from neutron star physics, from neutron physics, nuclear physics, we can't quite make a neutron star that small. So that leaves really black holes, okay, as objects that have in geometrized unit a radius comparable to their mass. For a regular Schwarzschild black hole, that's 2 masses. For a rotating black hole, that can be as small as 1 solar masses for the radius. A way formally you can describe this is as a compactness. So just saying, okay, let's take two objects. The radius of each is going to be something like 100 kilometers. Sorry, the diameter of it is going to be 100 kilometers for 30 solar masses. Right, one does times 5 kilometers. Solar mass times 2. Separation is 350. So this compactness, let's say R, is of order 1.7. This is much smaller than, say, Mercury and the Sun, the system that's 10 to the 7. Even the X-ray emitting black hole systems that we know have a compactness is of 10 to the 5, something like that. Even our galactic black hole, okay, we see eccentric orbits of stars around the central black hole of the Milky Way, and that has a compactness of 10 to the 3. Here we are at 1.7. Now you can try to see if this analysis, if you know more physics, you can see if this analysis is robust to changing other things. For instance, you can take eccentric orbits instead of the circular Keplerian orbits we've taken, just eccentric Keplerian orbits. What you get there is actually closer approaches to the black hole, because the Kepler's law scales as the semi-major axis, and the semi-minor one, the other side, you have a stronger interaction there. You could say what happens if you have spinning black holes. That changes effectively their effective size. If you have an extremal black hole, you can get as close to it. The radius is one solar mass, one black hole mass instead of 2. So the compactness would be 3.4, okay, instead of 1.7, but still quite striking. You could worry about physics that's not quite Newtonian. And we're going to talk about this because that's really post-Newtonian theory. But the relative quantity is b squared there. And b squared in this case is, well, the total mass over R is of order 0.3 at maximum. Okay. So if corrections should be at the 10% orders, kind of, just looking at that. So all in all, this looks like a very robust analysis, and it's also a simple one. And it's if you wish, it's in the alternative history where people built LIGO before we knew what gravitational waves were, and we had really Einstein's equations. The other thing you can do is a luminosity analysis. So try to figure out how distant the source is. And the best way to do that is from the luminosity again. So restoring a constant that we couldn't quite get from one-dimensional analysis, luminosity goes as G over C to the 5, which is very small, times the same combination as before of total mass, orbital separation, and angular velocity squared. You can actually maximize that if you take the speed of light, if you take Schwarzschild separation of Schwarzschild radius with units, and that is, if you do that, you get what's known as Planck's luminosity, which is one of those, it's a huge constant. Right? It's 3 10 to the 6, 10 to the 5. For binaries, there are a few factors that make it smaller. So you're not quite there. You're not at the speed of light. You're at 30% of the speed of light. The mass is, you get a factor for, we're not quite going down to Schwarzschild radius. We're at 350 kilometers and so on. But all in all, you can scale this up. And if we also use the other relation that we had, which was that the luminosity is proportional to the gravitational wave emission, gravitational wave strain. And if we notice from the plot that we top out at something like 10 to the minus 21 strain, that gives you a distance of about 45 gigaparsec, Hertz per max, 10 to the minus 21. Where, you know, this relation again stems from Kepler's law and the fact that the Chern mass appears in both cases. So we get something like 300 gigaparsec for a system. Another thing that you can estimate is the total emitted energy from the system, and that is going to be 0, energy at infinity separated, minus the total energy of the binary at the final separation. So if again you put in a various constant, you get something like 3 solar masses, okay, which is most of it emitted toward the end of the spiral. So this is a huge loss of energy. For instance, the sun over the whole of its lifetime will lose only something like 0.01 solar mass. This is 3 solar masses. You can also figure out what kind of luminosity that implies on Earth. And I think it's a fraction of a full moon, effectively, just over a fraction of a second, over 0.1 seconds, in terms of power. The fact that it was so hard to detect using 50 years of technology and so on for LIGO is because space-time itself is very, very stiff. So it's hard to warp it. Okay, so I think this went a little longer than what I was expected. As I was doing it, I realized that it's not quite at the 12-year-old level yet, but there's a lot there. And there's a lot you can see even from this, from just a simple plot of the waveform. And also it's why as soon as people in the LIGO collaboration saw that plot, like a few days or a week after the signal was detected, they basically knew what they had and they felt very, very safe about this discovery. So just the strength of that of the waveform was incredible, and although then we took several months to come up with a result, to establish statistical significance for alarm rates and so on. Really seeing that was very assuring and very convincing.
Sorry,
yes.
Go back to the
microphone. You have the ball? No, you have the microphone.
A question. Can you go back to explain delta E? What did you put as R there?
Something like the final orbital separation. So just so how much energy was lost to gravitational wave in total, with the idea that you start at infinity, you're shrinking this binary by gravitational waves, and so you just see what the final energy is. In practice, it probably loses more than that because the things don't end at the final orbital separation. At some point soon after that, you form a single black hole. The two horizons merge, You have an excited black hole, which is somewhat ringing. It must be ringing with its quasi-normal modes. I think we'll see it in one of the next few lectures. And it loses more energy to just settling down as a perfect curve, quiescent curve black hole. If you also do the numbers for a total mass of about 70 solar masses, the dominant quasi-normal mode would have a frequency of 260 Hertz. So it would have been visible in that plot, except that it seems to be a little bit under the noise. If you do the careful data analysis, you can you find a small signal to noise. You find not entirely convincing statistical evidence that you see it there. However, the analysis of these modes is going to be going forward for other signals as we get more sensitivity. Is going to be very interesting and very, very informative, because you see at that point the constants of the final merged black holes and not that of the two components. Okay, so going back on the main thrust of the course, to prepare for this, I took all the, not all, but I took several textbooks on gravitational waves. They're of order between 1 and 10. Let's be a physicist. Between 1 and 10 good ones. How about that? And see how they introduce gravitational waves theoretically. Okay, from equations, not that order of magnitude business. And more or less, it's always the same story, right? They copy each other. It all starts with Landau and Lifshitz, and you can do it. But I think I said, okay, not to be too boring, let's try to do it 4 different ways, quickly. Okay, so first one, we saw it by analogy with the electromagnetism. We think that there's something propagating speed of light, its second derivative, quadrupole, and all that business. Works fine. It even explains more or less the signal of the Ligo, so, but for a few constants of the order of 1. Let's try more formally linearized field equations. Okay, so we're almost in flat space-time. Oh, wait, okay. First, I need to remind you of all of GR in just one slide, since you there's not a lot there. I need to be reminded of this also often. So, okay, we're describing geometry with a metric tensor. That goes back to Gauss. You can do it all locally. That tells you everything. Okay, so there's a metric. It's got 10 independent components in space-time. We can also do in curve space. We're going to need a covariant derivative, because it's not clear how you compare vectors at different positions, so you need to transport them, move them. That raises the idea of a connection. If you want your connection actually to fit the metric, you're going to use the Levi-Civita connection, which then is expressed in terms of where's my hand there, in terms of Christoffel coefficients, which are derivatives, first derivatives of the metric, basically. From the covariant derivative, you also get parallel transport, how you move a vector, and you get the geodesic equation. So how do bodies, test particles, let's say, bodies that don't gravitate too much, move? Well, they try to go as straight as possible, following their own velocity across space-time. And that, so you're just basically taking a covariant derivative of their own velocity along the velocity, and that's just how you get geodesics. See, this is a reminder, it's not your fresher, it's not explaining any of this. There's curvature, however, right? So it's parallel transport is interesting, but it's not the whole story. You also want to see that if you parallel transport vectors along different trajectories, or you do a small loop, right? Transport the same vector along a small loop, you don't quite end up at the same place, right here at the bottom. So moving, let's see, this vector u along v and w and along w and v, you don't quite close up. The difference ends up to be linear in terms of the vector itself, not its derivative. And that difference defines the Riemann tensor. Okay, which here I'm writing in terms of the metric for coordinate directions. So the simplest way I can do. And now this idea of not closing up actually gets into the physics of test bodies by way of the geodesic deviation equation. Here the idea is that let's take 2 freely falling particles, each of them separately that are closed, each of them separately follows its own geodesic equation. if we look at the evolution of the distance of a little vector between them, well, that involves differentiating along the velocity and along this orthogonal direction. So naturally leads you to, again, Riemann's tensor. And so geodesic deviation, again, second derivative of the small distance between two test masses is proportional to their velocity and to their separation. And finally, we have the Einstein equation. So geodesic deviation is something that I met when I was in, I guess, in school with Filippo, but I didn't quite know back then. So you may not know, but there's an Italian writer, Italo Calvino, who loved to write about physics and about in a beautiful way, you know, very literary and so on. And he has a book called The Cosmic Comics, and one of the stories is he has this character called it's just a sequence of consonants, and so there's this short story which is about geodesic deviation, more or less, because there's three characters. It's himself, it's this beautiful blonde woman, and the colonel, is it? So some military men, and they're all falling. Okay, they're all falling freely in space. They don't even know where they're going, pretty much. They can't even tell if they're falling, which is general relativity, right? So acceleration is, you can take away acceleration by going in a local plane. And he's really hoping that somehow his trajectory will get him closer to the woman of his desires and not to the colonel. And so it's there, you know, getting all mad because he figures, because he thinks he sees them, you know, having some kind of secret signal. And so he says, oh, maybe, you know, in the past they were together and now they're floating away, but maybe she's coming to me. And so that was Calvino writing about geodesic deviation and about GR and about freefall. And I don't know if you read it also but back in those days, but so that's what it is. Now, moving forward, linearized field equations. So these are these textbooks, boring things, but just look at the left, look at the bullet points, basically. We start with a metric perturbation. You can have a formal parameter epsilon to say that it's small. So it's almost flat space time. So raising lower of indices you can do with Lorentz. Pretty simple. We can go to then form Riemann using the curvature in terms of curvature of flat space is 0, but on top of that we have this correction from the linearized field. Contract a couple of times, you know, from Riemann you get Ricci, from Ricci the Ricci tensor, from the Ricci tensor you get the Ricci scalar, and it doesn't look that great. Okay, you have all possible second derivatives that you can make out of this perturbation object. And so what does the theorist do in that case? Well, let's find a way to simplify it. How do you simplify it? Well, first of all, you define something known as the trace reversed perturbation. Just take the trace of the perturbation, subtract it out, but also then you use gauge freedom. Okay, so there are too many Einstein equations for the degrees of freedom that we expect to have. So in fact, the metric has, what did we say, 10 independent components. By the analysis of degrees of freedom, you need to go down to 2, at least in vacuum. So there are 8 gauge conditions, analog to gauge conditions in electromagnetism that you can apply. The one that immediately does lovely things for you in terms of the formula is a Lorentz gauge. I think it's Lorentz without the T. Is that Lorentz? Also known as a harmonic gauge. So that, together with this trace reverse definition, gets you down to a form that's basically D'Alembertian, happily so, is equal to a stress energy tensor, okay, which comes straight from Einstein's equations. And the way you apply gauge transformations in this linearized context is these are infinitesimal gauge transformations, which just look at, you need a vector field and you're taking symmetric derivatives of the vector field. So that's, and then in terms of this infinitesimal gauge transformation, just moving the coordinates a little bit, you just get a second order, again, elliptic equation for the that imposes this the harmonic Lorentz gauge. Great, a wave equation. We can write we can write a solution in terms of a plane wave. That's also what you do in particle physics. Out of this equation, you also, and writing a solution like that, you get immediately that the waves are going to be transverse with respect to the direction of propagation of the wave. And then you still have four gauge freedoms that you can impose. So we can use one to set the trace of the perturbation to 0, which is nice because then trace or trace reverse doesn't matter anymore. And we can use another one to zero out the vector, let's say, and the time components of the metric tensor. This is known as TT gauge for traceless transverse. And I'll show you in a slide or two that it connects immediately to the experimental phenomenological interpretation of gravitational waves. But we see here, so going back to the geodesic equation, so whether you fall away from your friends or enemies in space or you don't, you get that the only coordinates that end up mattering in this gauge are the space-time coordinates, and that these are just simple second derivatives of the metric perturbation field. So that's directly physics, because as we see, that's what you measure, okay, the geodesic deviation. So just summarizes, Einstein field equations turn into a wave equation for a metric perturbation. There's a great gauge that lets you, that the harmonic, and even better, you go to TT gauge and you have an even simpler description. Okay, alternative way of doing it. This comes from a textbook that actually Kip Thorne wrote but never published. But you can get on the internet the scan, or actually, yeah, a PDF of that thing. And it goes as follows. Okay, we can get equations for the metric. The metric, however, is a bit of a strange beast, right? For one thing, you can change it by doing gauge transformations. And so you don't really know what you're doing in some way. And then it connects to experiment, but you have to do it in a specific gauge. You have to take two time derivatives. So in a sense, you're doing physics using a potential, whereas if you're really an experimentalist, you should be doing physics using the field. What is the field in this case? Well, the field is Riemann. Why is Riemann the field? Because because of the principle of equivalence in general relativity, you can always basically zero out your metric and even your metric perturbation by going in a local rest frame. In a local rest frame, locally, everything looks like Lorentz, like Minkowski space-time. To see curvature, you need to look at your friend. You need to look at the geodesic, at the frame a bit removed from yours. So alternative, you can look at expanding out the metric, the description in your local frame to fill out space-time around you. The way you do that is with Riemann. Another way of saying it is that if you're in a local rest frame, you won't feel gravity directly because you can always be freely falling and therefore zero it out, but you will feel tidal fields. You will feel derivatives of the gravitational field, and that is Riemann. Okay. So now what can we do with Riemann? So one thing that's nice is that for a linearized field, Riemann is actually gauge invariant. The description, this combination, if you apply an infinitesimal gauge transformation, just ends up onto itself. That is desirable. We're speaking about a physical effect here and not just gauge. Riemann has lots of symmetries. It's for indices. As you twist them and exchange them, you get anti-symmetry in, let's see, the second and third, which tell you which are the two directions that you're doing the parallel transport game. Also the first and the last, if you conserve the metric. So if you're in a Levi-Civita connection and you transport the scalar product of two vectors, you need to close up. You need to get the same result no matter where you go. And that gives you that. And then you also have an anti-symmetrized, here the square brackets are anti-symmetrization in terms of those indices. So you take all the permutations and give it plus or minus depending on the sign of the permutation. The first Bianchi identity can be visualized more or less like this. Okay, so if you do parallel transport of vectors along 3 paths, you went, sorry, 1, 2, 3, yes, you have to close up just symmetrically. The 3 differences about transport along 2 directions need to make a triangle. And that's, I think that's almost automatic to first order, right? To leading order. What's more interesting is the second Bianchi identity. Okay, so if you go to Kip Thorne's big book on gravitation, there's probably like 20 pages about it. And the second Bianchi identity, or the differential one, is you add one more index, and then do an anti-symmetrization with respect to the last 3 indices in this case. And the way you can interpret it is that as the fact that you're doing again the parallel transport of a vector, which one, A in this case here, along all possible faces of a cube. That's because of the anti-symmetrized combinations of indices that you get. And if you do that, and you sum everything up with the right sign, you need to end up with 0, effectively, because in every side that you parallel transport on, you do it in 2 opposite directions when you combine all these paths. One can also be fancy and describe this as the boundary of a boundary is 0, right? That's Wheeler writing in the gravitation book. You can also write everything in terms of differential forms, and then you can write Riemann as a differential form with some manipulations. And then again, second Bianchi identity is just d squared of the field is 0. So these symmetries together imply that the Lambertian of R of the Riemann tensor is 0 in vacuum. Okay, and there's a formula. You can do the same analysis more or less in parallel for the electromagnetic potential, which also you can write as a form. The Faraday tensor is in a sense analog to Riemann, except it has only two indices. And again, you get that the waves follow because of some kind of dissymmetry. Okay, the only way once you're taking this symmetrized combination of derivatives, you move a little bit in space and in time, and you need everything to match up and to adjust. And the only way is for a wave to keep generating itself and to keep solving the wave equation. Okay, so now we see all the symmetries that we have and the vanishing of Ricci, Einstein's equation in vacuum. We again have wave solutions to these wave equations, plane wave solutions to these wave equations. And again, we have a transverse waves. And you can see that the only non-zero components are going to be, yes? Oh. Question.
Yeah, I wanted to ask when you said the Lambertian is with gravity, with the
no, because it's linearized.
Connection.
It's linearized. So
it's linearized.
Yeah.
Okay.
So if with a caveat, but if you're linearizing around flat space, then you could carry along your perturbation coefficients and through everything, and then basically you'd have some h² terms in that carried on by the covariant derivatives and so on. But the idea here is to keep everything at first order.
Okay.
With respect to h. However, one of the strengths, so that reminded me, one of the strengths of this analysis, this derivation by way of the Riemann tensor, is that I think there's a couple of papers by Wheeler in the 60s that they show you can do this not necessarily on space-time, but on curved, not on flat space-time, but on curved space-time, if you have a separation of lengths, of length scales. So if you have a small scale perturbations on top of long wavelength curvature, you can still do this expansion. You can still the Riemann symmetry still apply because they're linear, you know, and you still, and then you get a wave equation on top of the curve background, which will use then the background, the curve background derivatives, covariant derivatives, and therefore D'Alembertian. And so, and then the perturbation parameter, it's also proportional to the ratio of the two length scales. And then gravitational waves follow like a geometrical optic. You know, they also fall. They also fall along geodesics, basically in all geodesics.
Michele,
yes.
This equation holds in vacuum, right?
Yeah, because and that's what gives you the flat space. Sorry, the plane wave solution. You'll need something else to generate waves. Otherwise, you need a source term.
And okay. So is there an equivalent of the D'Alembertian H equal to T mu nu equation, or in this case?
I think so. It would involve derivatives of probably a second derivative of T mu nu. I think it's probably it has to, right? Yeah. Okay. Again, you can go to, you can figure out here. What's interesting is that you don't even need a special gauge. Just by all the symmetries, you figure out that the only non-zero components for a plane wave propagating along Z, let's say, are going to be XX, YY, and XY, and YX. So the choice of transverse case is kind of implicit in working with the Riemann tensor. And then you can define actually gravitational waves as the second, as something that integrates up to the Riemann tensor, so that this second derivative of H is the object that appears in the geodesic deviation equation. Basically, a short summary of what I just showed you. And now, final one. So this is a bit the this is for the theoretical physicists, but it also ties into something we'll talk about maybe in lecture 3. I don't know, which is the effective field theory approach to computing gravitational waves. So if we're really a theorist, all we know is the action. Okay, all we need is the action. So well, you're going to have your test particle action. This just describes free fall. What is it? Covariant transport of the velocity, geodesic equation, and then the Einstein-Hilbert action in terms of the metric determinant and the Ricci tensor. And now, if again we expand everything linearly in terms of perturbation on top of the field, you have a minimal, if you wish, coupling here to the velocity. You get the 1/2 from the square root. And then in the right gauge, in harmonic gauge, which you can apply with you know, your gauge fixing action term, and which is the most pleasant, you get something like a D'Alembertian. Here it's covariant, right? It's two ordinary partial derivatives of the field. This is the only, in this gauge, the only term that's quadratic in the action. And there's a big projector in front of it, which is what gives you again the formula simplifying trace reversed combination, and also it kind of enforces the transverse character of gravitational waves. So you take a second functional derivative of this with respect to the field. This is already in momentum space. The inverse of these derivatives is basically what defines the propagator, which looks very familiar, right? Other than the constant and this projector that needs to handle all these indices, it's really like the photon, really like electromagnetic waves. We'll use a variant of this in the analysis of gravitational wave generation from compact sources, but I don't know, my naive interpretation of the theoretical physicist mindset is that this is all I need, right? I don't need to know about binaries or things or linearized equations. we've got the action, we can go from there. Okay, and you can also, the arguments why this is a spin-2 massless field. We saw the minimal coupling to matter. So it, at least at the linearized level, it looks all benign and rather familiar. Of course, general relativity is nonlinear, and then there are more fun effects that come into play. Okay, so how are we doing on time?
7 past maybe after
want to take a break?
Relativity you stop.
Yeah, I can take a break. Okay, let me just go through this quickly. We were talking about the Riemann tensor and geodesic deviation equation as the dominant, the leading order physical effect that you can see. What's also intuitive is that it's a direct parallel to the effect of tidal fields in Newtonian physics. Newtonian physics, a second partial derivative with respect to space of the Newtonian potential gives you effectively the geodesic deviation, the relative acceleration between particles at nearby positions. It's what gives you tides on the Earth, so really is a tidal field. So the second derivative of Newtonian potential maps directly to the time-space component of Riemann. In fact, if you do formally the Newtonian limit of GR, that's also, you find that correspondence directly, and you can write. You concentrate your. You put your Newtonian potential in the G00 component of the metric, and that gives you this component of Riemann. That's all there is to it. So you can notice that this is not GR, right? This is any metric theory where you have free fall, which is any metric theory, really. So you can formally define gravitational waves in any metric theories before adopting Einstein's equation. You still have this relationship between these components, transverse components of Riemann and accelerations, and you can use that to write your effective gravitational wave as a second, the other way around, as something whose second derivative gives you Riemann. And, two integrations. So if we integrate the geodesic deviation equation for two particles that are together at start, then their separation as a function of time is going to be directly proportional to gravitational waves. Okay, so this H that we have either for Riemann or for the linearized equations and so on maps into a strain, maps you into a fractional deviation, a fractional variation of distance between local particles. And then you can do these classic plots where you say, okay, let's assume we have a circle of particles freely falling in space. What happens to them if you have a plane gravitational wave going along them? If you don't assume general relativity and the Einstein equations, you don't get this constraint that it's only xx, yy, and xy, xy that can appear. And actually you get 6 possible polarizations, okay, six possible polarizations of the field. The 2 are the classic ones, plus and cross, x, x, y, y. This you have in GR. If you go beyond GR, you can have a transverse effect, which would act on particles in a circle by, growing and then shrinking the circle itself. You can have 3 polarizations that act either longitudinally along the direction of propagation or in a combined longitudinal transverse way. So these are things that, you can try to see. You can try to test LIGO's signals to see if there's any evidence of these degrees of freedom. They're actually pretty hard to get theoretically from just theories of gravity. Maybe transverse spin 0 is the one that you get more easily if you do a scalar tensor theory of gravity. But even then, it's hard for it not to be really suppressed compared to the transverse degrees of freedom. So the effect of this is again this thing that I was showing also the 8-year-olds and the 12-year-olds, is that you have a circle, it gets squished, and then squish in the other orthogonal direction for a plane wave, and then you have another degree of freedom that does the same thing but turn 45 degrees with respect to it. Yeah, same thing effectively. This shows you the motion of the particles on the left and the effect on a circular particle. And this is something that you find in 25% of all papers about the gravitational waves write this. You take two tensors that define your polarizations, plus and cos, and then together you can use them to reconstruct the Riemann 0I0J, the spatial part of Riemann. There's a symmetry as you turn, your system of reference transverse to the direction of propagation. You just get a standard rotation of the polarization tensors with the 2, which is because they're spin 2, right? So if you go 180 degrees, you end up into themselves. Now, what's interesting, we were talking about proper reference frame, right? The fact that if you're locally flat, you're going to have corrections that come in Riemann times the second powers of the coordinates. Proper reference frame then is, and then compare that with the TT frame, which is the frame that basically simplifies the equations as much as possible and gets you down to a pure wave equation for the gravitational field. That's kind of interesting because it poses a mini paradox. Okay, one of those things that are not even that paradoxical. But if you're in TT frame, the geodesic deviation equation actually comes to nothing. Okay, and so locally, is that correct? Yes. Locally, all particles are freely falling. Actually, in this frame, they even keep the same coordinates as they fall. So there's no formally, you're not getting closer in terms of coordinate to your friend. Instead, in the proper reference frame, you do have a proper tidal field, tidal effect. So you can, you can be sitting there. You look at the other mass in LIGO. You look at Ursula, the friend in Calvino's story, and there's an effective force, in effect, that acts on your separation, and the force is proportional to Riemann and the second derivative of the metric tensor. So how do you reconcile those things? Is there a force or isn't there a force? Experimentalists really like the idea of forces because they look. Because if you're doing LIGO, okay, you're going to have local Newtonian forces, you're to have tumbleweeds, you're going to have thermal excitations and so on. So it's good to describe a force and to be able to talk about forces that move your masses. Whereas in the global frame, there's no such thing as forces. But the point is that all you can really measure is the distance between test masses or the distance between observers as measured by light. Okay, that's all there is in relativity, in special relativity. And if you measure that distance, in both cases, you get that it's proportional to, well, to 1, because if a space plus geometric perturbation. Okay, in one case, because there's really an acceleration and that the test mass is moving. In the other case, because it doesn't look to be moving, but actually you feel the effect of the metric between the two test particles, and therefore the distance measured by light has to be proportional to that, and again it comes down to the same number. So this is, resolution of mini paradox and a demonstration that in relativity it's useful to take many relative viewpoints that in the end, however, must come to the same physical effect. Okay, so that's the end of maybe 2/3 of this lecture. So it's if we want to break for.
I don't know. If you want a break or should we go on?
We'll end up earlier if you want a coffee. Okay, so to begin, can I ask if there are questions both here and remotely? So Riccardo, you would see them by text if there are questions, or
yeah. They can also speak.
Okay. So remote audience, please, if you have questions about the first hour of this. But only if there's any locally, we can, as I said, let's try to keep this interactive so I can also change future lections or direct them as appropriate. So Riccardo, if there are any, just interrupt me. Okay, so for the final part of this actually will get much less formal and more a quick story of where detectors are right now and where they were. So well, we've had gravitational wave detectors for a while. Joe Weber started making his resonant mass detectors, what was it, late 50s, beginning of the 60s. For a while, he thought he had seen even a signal, and there was a big historical episode there and a big debate. Now, as I was trying, so a resonant mass detector, how do they come about? Perhaps the force picture of the local reference frame where you have tidal forces is leads you to say, well, if I'm going to have some system, it's going to be stretched and squeezed. If I have an elastic system, and if it's going to resonate and to vibrate in its fundamental modes. So you want something big so that you magnify your force, since it's, as we know, is proportional to strain times length. You want a system that rings really well, so a quantity that ends up be very important is the quality factor, which is more or less the number of cycles that the excitation of a system will continue once you ring it. Now, those equations, you don't copy those down, because all they are is basically a forced oscillator. Okay, oh, here's my pointer. Okay, so I was actually going back and forth a little bit between textbooks here, and so one that I was telling Filippo is a pretty good textbook right now. Gravitational waves is Anderson. It doesn't go into resonant mass detectors very much, because you know, you can do this very quickly, but then you have to start saying, okay, then there's thermal noise, there's going to be some fundamental excitation of the resonant modes, and so that's what going to set your sensitivity. If you want a full discussion of the physics of these detectors, instead you need to go to Maggiore, who does it pretty well and very formally. In practice, you see here Weber is touching his detector, which means that it's at the room temperature, and so it's going to be pretty noisy. Okay, it's not that huge either, and I think these are either capacitive or magnetic readouts, so the way in which you see how much it's the thing is vibrating. So the sensitivity for this would have been limited, would have been at maybe 10 to the 18, 10 to the minus 19 strain at its best frequency of maybe 1500 hertz. Modern detectors are quite a bit more sophisticated. For one thing, they're cryogenic. You know, one of them had a claim, I forget which one, if it was the Italian one or the French one, to be the coldest object in the universe. At coldest, you know, macroscopic object in the universe is something like 15 microkelvins, something crazy like that. And also, you want to experimenters are being very creative in detecting, in measuring the excitations of the detector. You attach piezoelectric, I think, systems. So it's basically another forced oscillator coupled to this one, and then there are superconducting amplifiers attached to it. Even that, they can almost get to the level of the interferometers in a narrow band centered around its fundamental frequency. And so I feel like you know that they're beautiful experimental objects. They too bad that they couldn't quite compete. They're just off maybe by an order of magnitude or two in terms of what was needed to see a signal. There are still there are spherical detectors, right, in development. There was one in Brazil for a while. Those have some superior qualities, some interesting points, because they also see all possible polarizations of the field, but I haven't heard very much about them. So that's good for my lectures, because actually resonant masses spoil a little bit my big scheme paradigm for the description of all gravitational wave detectors. In the title, I promise a universal theory of detectors, and that's really they're about time transfer. Okay, so forget masses. We're talking about transferring time between freely falling test masses, or things that we can approximate as being freely falling, and that covers everything. It covers LIGO for sure. We're using light to measure a distance, relative distance between test masses. It covers LISA, where the spacecraft are literally test masses falling in solar orbits. And again, we are measuring the distance between them. It covers Doppler tracking, which is the idea if we have a spacecraft that we're sending to Saturn, one day to Neptune, we can send up a signal, a radio signal, get it back, and again, look at the round trip time. And it does cover pulsar timing, except it's only one way. Okay, we're not getting back a signal from the pulsars, but we're getting something like a clock from pulsars. And in all cases, the relevant formula is just that the time of flight is going to be what it would have been without gravitational waves, plus a component that's here I haven't done the square root already of the metric, so it's 1/2. And then some kind of projection of the gravitational wave tensor along the propagation word line, dotted into the direction because of the transverse nature of the waves. In practice, it's ended up being very convenient also to take a derivative of this relation. And if you have a derivative, then you basically see just the edges of the propagation, and you will see a difference of the gravitational tensor at the wordline event, where my laser signal, my clock signal was emitted, minus the field at the point of reception, again dotted into geometric factors and divided by something like a Doppler boost. And now this is your fractional frequency perturbation, and it looks like a Doppler shift, effectively. Okay, so you can look for it with the same experimental techniques. In LISA, for instance, you'd see that the incoming carrier phase of the laser beam experiences an instantaneous Doppler shift that is oscillating with the gravitational waves. Okay, good. Now, universal theory. So universal theory of gravitational wave detector sensitivity. It must get better before it gets worse. So, which is, I hope, it's not also a philosophical statement about life or about current politics, but it may be a statement about any physical experiment, really, because you have a band where you're trying to get things as good as they can, and noise inevitably ends up being worse on both sides, in frequency in particular. Now, what limits, in all detectors, what limits you is, on the one side, the fact that you cannot measure the distance very precisely, the distance between falling particles. In detectors that use light, and interferometry in particular, this imprecise measurement is at the end due to just the quantum nature of light. So the fact that with a single photon you can only measure a distance roughly to its wavelength. If you have many photons, you can get the distance to something like the wavelength with the square root of the number of photons, and that gives you a square root of power, right, for the laser light that you get. Let's see, for pulsars, more or less the same story. It has to do something with the intensity of the signal that you're getting, although there are also considerations about the stability, right, of the signal itself. As we go to low frequencies, instead, what dominates is the fact that you don't get perfect free fall. Okay, everything is accelerating because of things that are not gravity. So for LIGO, it's going to be thermal noise if the test masses are not cooled to 0 Kelvin, which they're not. It's going to be seismic noise that you cannot quite filter out, although you're doing your best with suspensions and with shielding. It can be a residual Newtonian noise just from things that are moving nearby, including the Earth itself. And in a kind of like catch-22, it can also be radiation pressure. So the fact that the same light that you want to be very powerful so that you have lots of photons to average out the measurement of the distance is also pushing in a quasi-random way onto the... so the two things together are a balance, okay, radiation pressure in LIGO and the measurement of and the reduction of shot noise, and which give you also together, we'll see next time, I think, something called the standard quantum limit, which is the best you can do if you're measuring distances with photons. In the end, for LIGO right now, the one that you really can't beat at low frequencies is the seismic limit. Okay, so I'm already telling you a lot of, I've already told you a lot of this, but basically ground-based interferometers, there's what you're measuring is a relative phase change. You're using interferometry not because interferometry is necessary to measure distances, but because interferometry cuts out the your basic clock noise. So if you knew you were making perfect waves, laser waves with the accurate to a part in 10 to the minus 20 or so on, you could do one-way measurements of distances. But because you're going to have some kind of random walk, some kind of noise imposed on your frequency or your length scale, one way you can cut that out is by doing interferometric measurement and sending light along two paths, getting it back, and that way you can you cancel out effectively this common mode noise, which is the intrinsic noisiness of the frequency reference. Space-based interferometers, pretty much the same thing. The measurement is very similar, again, shot noise. The details are a bit different, but for space-based interferometers, the interferometers is the system, LISA, is bigger than a wavelength, the typical wavelength of the gravitational waves. And because of that, you won't probably use the description in the laboratory frame with just the effective force. You want to be in the TT frame and compute metric perturbations. And then pulsar timing, again, same story more or less. I'll talk quite a bit of this again, but their imperfect free fall also means the fact that a neutron star that is emitting radio pulses is not quite a point mass. There's going to be some kind of geometry, some stochasticness due to the emission mechanism, and where really you can reference your wavefronts. Altogether, you have a gravitational wave spectrum with several experiments that are trying to get at it. The part that's that's been explored, let's say, and that will continue being explored, is the highest frequencies where LIGO is sensitive at about 100 to 1,000 hertz. It's interesting that this plot seems to have 2 10 to the 2. 10, 10 to the 2, 10 to the 2, 10 to the 4. So, how would you do that? So there was a human hand. There was a human hand here, unless it was a 2.9999 that got average, that got rounded down. So that's where you see stellar coalescences. Okay, so if you want to be above seismic noise, that's where you end up with systems that can support these kind of frequencies, and that's small stars. If you want to go to big black holes, okay, so the things that are at the center of our galaxies, or you want to go to binaries that are still separations that even white dwarfs can sustain, well, then you need to be in the millihertz band, and that's where LISA aims to be. We now have a 2035 technical launch date. A political launch date may be a little later, but as Antoine can tell you, we're marching towards executing the mission, so we'll be there. So LISA sees big black holes merging, which scales up the signal by just the factor of the mass ratio. It sees galactic binaries. We think we have many million in a galaxy of white dwarf binaries and so on. It sees MRIs, which are small black holes inspiring into big ones. It also sees the beginning, let's say, of the stellar mass binary coalescences that LIGO has seen already. So in fact, GW 150914, the first LIGO detection, would have been probably a LISA detection if LISA had been on in 2012. okay, about 3 years before, since it takes about 3 years to go from the millihertz and so on. And now, if you go all the way down to pulsar timing, now we're talking of a detector that's, in some sense, the size of a galaxy. Your emission of pulses is at 1 kiloparsec away, and there you're much less sensitive. See, so the actual shift in frequency or in distance that you can resolve is only 1 in 10 to the 13, 10 to the 14 parts. But luckily, we have huge black holes there, 10 to the 9 and so on, and 10 to the 10. So everything scales up by the chirp mass. And so we have a hope of seeing some signals soon up there. Altogether, just like there's an electromagnetic spectrum, there is a gravitational wave spectrum with different sources and different experimental techniques. At the very bottom end, I don't know very much about them, but you can see the imprints of the gravitational wave on the CMB, and through, in particular, the polarization signal, there was a temporary detection there. There was a claim that later ran into the problem of having mismodeled the foreground. And that's outside of the plot and outside of my expertise. But if Filippo, for instance, wants to talk about it, we can arrange for that. You don't need, this was going to be a movie, but it's not, because this is a PDF, but better. So since I'm late, but I told you already, basically. Ground-based interferometers, the basic principle is the Michelson interferometer. In practice, maybe I can show you some equations next time. Even a Michelson interferometer doesn't quite get you to the 10 to the minus 21 that we needed to see GW15 on I-14. Because you can make power laser, you can make maybe 20 watts. That's already a pretty sizable laser. That's not enough photons to get you down there to average out the shot noise. What then LIGO does is, for one thing, it makes arms into fabric Perot cavities so that power can be recirculated, and that extends the effective length of the instrument. Although the arms are 3 kilometers, they end up looking like 300 if your light is keeps circulating. And also there's a signal recycling, another mirror that creates an amplification of the signal. You don't know, yes?
Michele, just, so this signal recycling has been always there from the beginning of LIGO. It's not something that has been put later or something, I don't know. LIGO has been planned like that, or?
Yes, although it's a tunable parameter. So it's possible that when it started, I can look into this. It's possible that when it started initially, it was it has to be in the optics, but you can change what it does effectively, because what signal recycling does is to kind of move around the sensitivity that you have and the noise to different frequencies, so that you get better. Where the thing that was only more recently demonstrated and starting to getting into LIGO more is quantum squeezing, which is the idea that the fundamental quantum noise that you have in your photons, you can reshape it in a way that you get less phase noise and more number noise, basically. So story of LIGO, well, you don't need this. So as I was telling you, it was promised to be, advanced LIGO was promised to be a 2005 thing when I was in grad school, and then it didn't quite pan out. But it's very impressive. If you get to visit either LIGO, one of the Virgo locations, for one thing, the fact that you have to drive along the arms and not just walk is impressive. They're shielded. They're in this high vacuum tube. It also doesn't look like much if you expect lots of laser beams and so on, because it's all sealed inside those these big tanks. And plus, it's an infrared laser, so you wouldn't see it anyway. Although it would blind you if we put it. So multiple stage, isolation. There are these multiple pendula, inverted pendula. This is something that the Virgo was especially strong on, and the Virgo technology was brought to advanced LIGO to get more isolation at low frequencies. Very smooth masses. At some point, silica, then sapphire. there was a fun episode of this American TV show Numbers, where many years ago there was being shot at Caltech, because Caltech makes money by renting out space to Hollywood, which is just nearby. And so there was one episode where they were stealing the LIGO sapphire test masses, because they're sapphires after all, right? And therefore very, but and it was the local theoretical physicist actually who had them in custody, and he would take them every day and put them in a safe, and because they're sapphires. In practice, you know, they better not get dirty, and they're in high vacuum. You need the surface to be extremely flat, and so on. So sensitivity, this shows design for LIGO versus what they obtained in 2015. I think right now for the next science run, which is going to start in approximately November, I think, October or November, joint with Ligo, Virgo, and also Kagra, the Japanese detector, somewhere in between, still not a design. But there's quite a bit of R&D already for the successor to this generation of detectors. These are known as 3G for third generation, so not the initial ones, not advanced. And ET is the European concept that is LISA-like, right? Would be a triangle of 3 interferometers under a mountain, probably in Sardinia, right? So we think. Voyager and C, Cosmic Explorer, are the two US concepts for the moment. They're just concepts, you know, they are studies. There's not even much funding yet for them. The difference, Voyager would be in the LIGO civil engineering facility. So the same cavities, the same buildings and so on. Cosmic Explorer would be something like a 40-kilometer, right, interferometric detector to put in some mine, probably underground. And
sorry, Michele.
yes,
it does seem that Voyager is so good in sensitivity with respect to ET or Cosmic Explorer.
No, it's not, because it's as I was saying, it's not cryogenic, it doesn't go underground and so on. So, but it's still a factor of about 4 to 5, depending on frequencies.
Okay, so it would be faster to make than the others.
It would be, it's the most I think they could push the current facilities, because certainly, you know, digging 40-kilometer tunnels is a big deal. Whereas just replacing all the test masses and the lasers and so on in the current one is.
Sorry, what is ASD? I don't understand. The y-axis.
So as this amplitude spectral density. Okay, so the way you end up measuring noise is by noise power reflected in your measurement observable. But since we tend to like to talk about the metric perturbation h rather than the square, then you take a square root and see that's why it's 1 over square root of hertz instead of being 1 over hertz, which should be a power spectral density for a dimensionless excitation. But you know, some people just do the square of this plot effectively and do PSD, and then it's 10 to the minus 48, and it looks more impressive. But it's all the same. And then this is the International Gravitational Wave Network. The 2 LIGOs in the US, Virgo, as you know well, in France and Italy. Kagra is the Japanese detector, which is in a mine. It's underground. It's cooled down. It will be in operation starting in November, simultaneously with the other. But the range and so the sensitivity, which are the inverse of one another, is only, I think, it's probably a 10th to a 20th. So it's still not shaken down in terms of noise compared to the others. Geo600 was not quite a prototype, but was a detector that was run in Germany for many years, and that was the most advanced one in terms of optics. I don't think they're running right now, but unless they are running, Geo's running. And then LIGO India. So what happened is that there were really 3 LIGOs for a while. So at least in the initial runs, there were 2 LIGOs running at Hanford, one on top of each other. But it's much better to have one of them elsewhere on Earth. For one thing, the triangulation really improves a lot the most you have. It would have been even nicer to have in Australia, just in terms of the geometry of triangulation, but that didn't get funded basically. So now the agreement is between the US and India is this basically India is going to work out all the, again, the civil engineering, the buildings, and the personnel, and the actual experiment itself, the test masses and so on, are going to be just brought from the US and built there. I think it's progressing, but it's probably several years away from first light. And then I'll probably going to end here with the science goals, and we can talk about space and pulsar timing at the start of the next lecture. Science goals from LIGO and Virgo. I think this slide actually is from before 2015, so it could be changed by doing little check marks at the items that have been done. We'll talk about this, but primary source is stellar binaries of black holes, neutron stars. All combinations have been seen at this point: 2 black holes, black hole, neutron star, 2 neutron stars, including an exceptional one that also had lots of electromagnetic fireworks. We'll talk about that. So you want to see many of these so that you get an idea of the rate of mergers and parameter distributions. With neutron stars, you can probe the neutron star equation of state by seeing the first effect of non-point-like mass effects on the merger. You want to test GR, see if the waveforms and the dynamics that you get are really GR. So this part is all in progress, okay? Lots of papers about it, there's data, there are results, including the GRB link, the link from gamma ray bursts to neutron star mergers. The rest actually is still waiting for nice sources and signals to be seen. Bursts are things that are short and not quite, they're not in spiral chirp-like. You'd get them from supernovae, massive star collapse. You get them from more shorter encounters of black holes, either only the merger, not the spiral part, or an eccentric encounter where it's just a flyaway. Basically, you get just one hyperbolic orbit. Let's say you get a little burst of radiation. Cosmic superstrings, maybe, if they exist, they look nice in theory. And then you can also see individual neutron stars if they're sufficiently deformed in a quadrupolar fashion with respect to symmetry. These haven't been seen so far. There have been some interesting upper limits posed on the deformation of stars, but we can talk about that too. And of course, cosmology and astrophysical stochastic background. Astrophysical, we may get to see at some point a background from black holes, just the fact that there are very many out there too far to be seen individually by creating some kind of noise background. The cosmological things for LIGO are probably not very relevant unless you're in some very weird, Filippo knows about these things, but in inflationary scenario, just because you're very high frequency and it's hard to keep much power there. Okay, so then we'll move on to Lisa next time. I made 12 after all. I didn't think I would. So if you have quick questions, otherwise you can also ask your question now and I can answer next time perhaps. And thanks to all, even our YouTube viewers, and see you next week. Oh yeah. You're far. Yeah. Probably want to go to lunch, but
No questions. There is some questions.
oh, cool.
There is about the
Still typing?
No, no.
It's gone away.
Thank you, Professor.
Oh, I'm no professor.
So, okay, so we will stop here.
Okay.
So,